All right, because the other recording did not record the entire thing because I think I accidentally hit the hotkey for the pause button. So I'm gonna redo this whole thing. Well, I'm not gonna redo the entire thing. I will start to re-record about 10 minutes into the lecture. Obviously, I cannot remember exactly how all the material got covered the first time. So that means, what I'll do this time is to try my best to reproduce the content that we actually did go over in class, but it may not be exactly the same way. But I'll give it a try. So let me check to see which is being done for this class. So it's not this node program, and just looking through. Okay, I might be using the wrong command line window, but that's okay. I can find the program. I think for this Tuesday, Thursday class, we were using struct.c. Let me just double check. Um, Actually, no, I take it back because I know I created a folder, which is the singly linked list. And let's see, what was the name of the subfolder? Um, Traverse, that's it. Okay, so we go into Traverse, and then let me open up both at the same time. So just like what I did in class, I'm going to try to replicate the same process. So, um, all right. So this means I have that file also open in a different window, and this is the one that I was using on the other day. This is the one. So what I would do, that's not the content that I wanted to do, and this is the one. Okay, this is the correct one. So I'm gonna have to get out of this editor first, and then go back into this editor. Bump up the font size just so that it's easier for all of us to see the text, and a portion is out of the screen area because this is not the same setup as in the classroom. So I kind of have to readjust the size of the window to make sure they all fit within what is being recorded. There we go. All right, so give it one more try, and now we can restart the whole process. So I think about 8 minutes into the lecture, we were starting with traverse, and that's where we will start here. So I'm gonna look up, where traverse starts, line 37, and then we'll look up when it ends. That's when 37 to this line, delete. So now we're gonna restart from the beginning with traverse. Traverse has one parameter, and the return address, but has no local variables. So from the stack perspective, we have p as a parameter, and then we have the return address, each one taking up 1 byte on the stack. And in this notation, I always use the notation of whatever is in a higher memory location, which is p in this case, is at a quote unquote higher location, and then whatever is at a lower location, which in this case is the return address, is at a lower portion in terms of memory address. The next thing we do, the next thing that I do is to define the offset to each item. So, okay, I need to start with TLVS, local variable size. It's going to be 0. And then the return address does not need a label because I typically don't need to access it. So the next one is L underscore P, which is going to be L underscore LVS 1 plus, because this one here is accounting for the byte that the return address is taking. What that also means is at the entry point, this is where the stack pointer points to. The stack pointer is pointing to the return address, which means parameter P is at 1 byte away from where the stack pointer points to. So the displacement to find parameter P is literally just 1, but the way I compute this is relative to the number of bytes used by local variables, which in this particular function is 0. So now I can get into the code. The first thing we usually do is to allocate for local variables. Even though in this case we don't actually have any local variables, we'll still kind of go through the motion to do it. So we have TLVS, and then we subtract that much from the stack pointer, and then when we are done with the subroutine, we're going to do the reverse by adding that much to the stack pointer to deallocate the local variables, and then we go through the usual return code, which is LDBD. That will retrieve the return address from where the stack pointer points to, increment D, because that byte is no longer useful anymore. So we deallocate that byte from the stack by adjusting the stack pointer, incrementing the stack pointer by 1, and then the JMPB continue execution where register B is pointing to, and register B retrieved the return address earlier, and that's where we're going to go. All right, so that is done. So now I can actually focus on the code itself. So the first thing I see is we have a while loop. The structure of a while loop is we need a label for the beginning of the while loop, and we need a label to mark the end of the while loop. And then right before the end label, we need a JMPI, a unconditional branch, back to the beginning of the while loop. So all of this stuff here is based on the discussion when we talked about how to quote unquote compile a program from C to assembly language. So now we need to determine, the condition, and when do we stay in and when do we get out of the loop. So to determine that, we have to call cond first. So the way we call cond is to push the only argument on the stack first. So to access the value of p, we have to do LDIA or B or C, it doesn't matter which one, we just have to be consistent. So what this does is A is now containing the address of parameter P minus where the stack pointer is pointing to, because this is the displacement in number of bytes from where the stack pointer points to where we find parameter P on the stack. And then we add AD, in other words, we add the stack pointer to register A. So register A is now, what it had, but we also just added the stack pointer to it. So if you use algebra, you can see how that minus d plus d will cancel out. So now we end up with just the address of um, the parameter p, and then we need an LDAA to dereference. So now we are dereferencing the address of p, which is really just the value of p. So now we can push that on the stack. That would be a decrement D STDA, and then we can push the return address. And there are a few different ways to do that. We can decrement D LDI A dot write plus, and then STDA that pushes the return address on the stack. And then at that point, we can continue execution at the subroutine that we're calling. And then when we return, the caller is responsible to deallocate the 1 byte that is still being used by the parameter, the argument. So we have to use an increment D to deallocate that byte. So that completes the call, which means at this point, register A has the return value of cond, and we need to see whether it is 0 or not. If it is 0, we need to get out, because according to this loop here, we only want to stay in as long as cond p is returning a non-zero value. So to push the return value, which is now in register A through the ALU, we can use AND AA, and then we check the Z flag. If the Z flag is set, that means A is indeed 0, which also means the return value is 0. At that point, we can get out of the loop. So we can go to T while end, like so. And if we do not go to T while end and continue execution, that means we are now in the body of the while loop. So now we can look into the body of the while loop. The first statement has a P points to I, which is basically referring to the value of member I of the structure the parameter P is pointing to. So if you think about it like that, the first thing we need to access is going to be P, the value of P. The value of P is already in register A because, well, actually, I take it back. We cannot count on that. So let's go ahead and recompute that. So we have LDI ATP, add AD, and then we have a LDAA. So register A now has the value of parameter P, and parameter P, according to the type here, is a pointer to a struct X. So that means we now have the value of the structure in register A. But we are interested in accessing member I of that structure. So that means we need to load the offset from the beginning of the structure to member I, which is what X underscore I is representing. We need to put it into a register, and then we have to add register B to register A. And then at this point, register A has the value of, um, oh, I take it back. It doesn't have the value. It has the address of member I of the structure that um, P is pointing to. And since the right hand side, it does not say the address of, it says the value of. So that means we need an LDAA to get to the value of um, member I of the structure that P is pointing to. And now we have to deal with the left hand side. I cannot reuse register A, but I can reuse register B. So with a global variable like printer, the label itself is the address. So if I load printer as the label into register B becomes the pointer or the address of printer as a global variable. So that's pretty handy because now I can just store register A, which is containing the right hand side of the assignment, to where register B is pointing to, which is the global variable printer. And that concludes line 29 of the C code. Line 30 of the C code, the first part is really not that much different. In other words, I can look at these 6 instructions, copy and paste it, and then just change the reference of x underscore I to x underscore P. So let's go ahead and do that. So we have line 39 to line 64 and copy that to where I am here. And you can also kind of see where the dot notation is coming from, because in VI, dot is representing the current line, the line where the blinky cursor is. All right, so I have to remember to change this I to P, and you can now see that the two P's are different, because this P here is referring to the parameter P, this P here is referring to the member P. And in assembly language, you can clearly see that one is the displacement from where the stack pointer points to where we can find parameter P on the stack, and then the other one is the offset in number of bytes from the beginning of a structure to the member that we are looking for. So those are two distinct um, labels. And then we need to store that back to the parameter P. So if we don't mind recomputing everything, there's a way to optimize this, but we can recompute the whole thing also. So I cannot use register A because register A now contains the right hand side, which is the value of member P of the structure that parameter P is pointing to. So I can now use register B, and that's it. Okay, so now we have the address of P in register B. So we just need a single store in this case, and we are storing register A, which is containing the right hand side, to where register B is pointing to, which is the address of parameter P. So this is when we run this code, I will explain and reconstruct the stack so that you can kind of visualize what is going on when we have this code running. So right now, I think I got all the code, and then I need to um, get to the assembler. And there we go. All right, so it doesn't look like I have the assembler up anymore. Okay, so I'm gonna have to look into um, my drive, and it's gonna take a little bit of time because we are not uh, I'm not in the usual dual monitor setup that I use in class, so it's gonna take a little bit of time to get back to the tool that I need. All right, so now we're back to this tool and we want to get to the assembler. I don't need the assembler to do the assembling because I can use River Spider. However, in order to show you the actual result after we run this code, we still need the assembler as a spreadsheet to do that. So I'm going to pop up the source code first, and then we'll go ahead and run the code. So let me go ahead and make sure this is saved first, which is my favorite mistake of not saving first. And then we use River Spider to run this code from traverse SLL, which stands for singly linked list .ttp-asm. So I just need to specify where to find the TTP-ASM source code, and then the script takes care of the rest, including running it, collecting the trace, and putting the trace back into the trace raw data sheet. So now that everything is done, we get back here, and then we get to, well, I already know the source file does not have a assemble time problem, so we can now go to analysis. And in class, I also, kind of, there are a few things before we can actually take a look at this. So let's go ahead and talk about those few things first. The first thing is we need to know what we're expecting to see as the overall behavior of this code. I went over that in class by executing the C code by hand. So you can see how Traverse is using the address of A for the first invocation. So in the first invocation, P as a parameter is the address of A. So when we call cond P, which is really just returning P itself, um, it is not 0 because the address of A is non-zero. So now we get into the subroutine. The member I of um, global variable A is a 5. So printer should get a value of 5 first. And then we go to the P member of the structure pointed to by parameter P. And that would be, according to this, it's the address of B. So then P becomes the address of B when we get back to the beginning of the loop. The address of B is also non-null. It is not 0. So that means cond is going to return a non-zero value, which means we're going to stay in the loop. P is the address of B, and we look up the I member of B. It is 1. So the next value that printer should get is going to be 1. And then we do the same thing again. The P member of the structure that we know as the global variable B has the address of C. So that means at the end of the second iteration, parameter P becomes the address of C. Then we go back here, we check whether that is a null address. It is not, because any other than the null up instruction at the beginning of the entire program, nothing has a null address. So we passed that test already. We get back here, and we can also see how global variable C has an I member of 7, and that's what we are going to quote unquote print to the printer global variable. And in this time, we're also going to retrieve the P member of global variable C, which is 0. And this is how P as a parameter in Traverse is going to get a value of 0. So when we pass that value of 0 to cond returns just P itself, which is 0. And when you have 0 in a condition in the while, it is interpreted as false. And at that time, we exit the loop. All right, so at this point, we know the printer should get the values 5, 1, and 7 respectively. And we can check that first. Okay, so we will go ahead to go to the, oops, wrong thing. We go to the assembler. And the first thing I need to check is where is printer? And the quickest way to get to know where printer is to go to the assemble tab. And what we need to do is to look up, the local variable printer. The global variable printer, which is right here. And we can see how this byte 0, which is allocating for that byte for printer, is at location 03. So that means anytime we change printer as a global variable, it is location 03 that is going to be updated. So we can now go to the analysis tab and then do a control H to search. And I can now focus on any changes, okay, to location 03. I'm using a concept called regular expression because this way I can just search for a pattern, and then we are only interested in column C. So we can now specify, we only want to search in column C, and then we click find. The first update is 5, that is consistent with our expectation. The second value is 01, also meeting our expectation. And then the last value is 07, which is also meeting our expectation. So from the perspective of just overall checking whether the code is working or not, we now have confirmation that it seems to be working. But I do want to make sure that going to the end of the entire trace, I want to make sure that the stack pointer is balanced, which means I want register D to be back to 00 before we get to the halt intended halt instruction, which is right here. So all of those are matching our expectation. So the program is working properly. All right, so just because a program is working properly doesn't mean I'm done with explaining this program, because in class I specifically chose 6 instructions and go like, well, these are the 6 instructions we want to find out what is happening. So that's what we're gonna do. Okay, so we're gonna switch back to the source code and go to the 6 instructions that we want to focus on. Okay, which is from line 59 to line 64. So these are the 6 instructions that we are particularly interested in. So we'll go ahead and comment. Okay, so I'm going to comment. I will go ahead and comment what register A and B has at for each line of code. So register A is the offset of where we can find parameter P from where register is pointing to. So technically speaking, it is the address of P minus where the value of the stack pointer. And then on the next line, I'm adding the stack pointer back to this quantity. So I just use whatever A had from the line before plus D to it. But if you use algebra, you can figure out that this all boils down to the address of P. And then now we are dereferencing the address of P. The address of something and dereferencing that something kind of cancels out. So by this time, we're going to get the value of P in register A. Register B, on the other hand, contains the offset from where we can find member I from the beginning of the entire structure. So in this case, it does get a little bit harder to explain. The best way I can explain, is basically it is the address of member I of where P points to minus P itself, which is the address of the entire structure. So that's what B has at this point. And then we add B to A. So A is now, so if I work on this step by step, so register A is now P plus the address of member I of the member I of the structure that P is pointing to minus P. So let me just put some parentheses to explain what is going on here. So everything within this pair of parentheses is B, which is which I explained on the line before. So when we add B to A, we are basically adding this chunk of this expression to what we already have in A, and this is where we have A already has this content here. So using algebra, this P here is going to be canceled out by this minus P. So we basically end up with just the address of member I of the structure that P is pointing to. So now we are not exactly interested in the address of member I of the structure that P is pointing to. So we want to dereference it, and now A is the dereference of the address of member I of the structure that P is pointing to. And I already mentioned earlier that the reference operator cancels out the address of operator. So now we end up with the value of member I of the structure that P is pointing to. All right, so that is a lot of explaining, and I can also just kind of rerun this whole thing through River Spider, because this way, the trace that we're looking at is going to also reflect the comment, and this is one tool that I encourage you to use when you're studying, is to go to okay, so I need to find that line first, which is really easy to do as well, because if I go back to the editor, we can see that we are now dealing with line 59. So all we need to do is to look up column F and make sure that we can find 59 at least the first time. So we got 59 here. Oh, okay, I made that mistake again because I forgot to save the file first. Okay, let's go ahead and rerun it. I mean, between this one and the run before this, the only difference is the comment. But I do want to kind of make sure that you can see, how the comment is reflected this time in column G, and that makes it easier for us to figure out what is what. So this one here is indicating that parameter P is 1 byte away from where the stack pointer points to. The stack pointer is FE, so FE plus 1 is FF, and that's what we got in the second instruction because we add the stack pointer to register A. So FF is the address of parameter P. And then the next line does a dereference, which means we are now getting to the value of parameter P. And we can, later on, I can track down here why we know at location FF we have a value of 0.8. And then we load the displacement of where we can find member I from the beginning of a structure, and that turns out to be 0, 0. And this has to do with member I being the first member of the entire structure, because the first member of the structure shares the address with the structure itself, and that kind of makes sense, right? Because we don't want to waste some space, to make sure that the first member of a structure does not equal to the address of the structure itself. That just doesn't make sense. You're wasting any byte. So that's why the address of the first member of a structure is the address of the structure itself. Um, and then moving on, you're adding this displacement, which is 0, 0 to the beginning of the structure. Doesn't do anything because it is a 0. We're adding 0 to 0.8, and that's why A continues to be 0.8. All right, so at this point, I think it's a good time to take a look at what the stack should look like. It's harder for me to do the handwriting thing with and also use it as a computer at home because I'm using a single screen. So what I'll do instead is I'm going to use a spreadsheet program to help me illustrate what content is in RAM. So let me go to LibreOffice Calc. And obviously this is way too big for what we are doing. Let me change the size of that. All right, that doesn't seem to do it. All right, give me one more second, one more time. It doesn't want to resize. Um, hmm. Okay, let me minimize. It's not minimized. Oh, every time I do this, it is minimizing itself. All right, so what we need to do is I have to adjust this kind of the long way. There we go. Okay. All right, so what we want to do is to take a look at memory content from high to low. So we'll first designate the memory location first. So this is going to be location FF, and I can also use the tool. I can use the equation to do this. So we basically say dec to hex, and this is going to be location 255. So it's going to be 256 minus the row number of the cell itself. So now we can just kind of replicate this approach a few times. And I think we need to move it down to maybe this much. Okay. And then we can work our way from the bottom up. Okay, maybe that's too much. I don't think I need that much. Yeah. Um, right. Okay, I don't think we need that much. Maybe just up to F3. So what we will also do is to go from 0, 0, blah, 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 and then we jump all the way to 0, 3. The reason why I'm jumping to 0, 3 is because, okay, it doesn't like that because, the alignment is off because it thinks it is a numerical value. So I just need to kind of force the spreadsheet to know that this is not a number, instead it's a string. So the alignment stays consistent. So 0, 3 is where the printer is. And then we got 0, 4, 5, 6, 7. Okay, I'm just counting the number of bytes that I need because we have three structures. Each one is taking up 2 bytes. So we need 2 more bytes. So I need to designate the byte address for these guys. And this is just dot 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 because I'm not going to show the addresses of locations that do not matter in this case. So we want 1, 5 to be, okay, let me do the counting again. It's a 0, 3 plus 6 minus 1. So it's going to be, this is going to be location 0, 8. Okay, does that make sense? Okay, this is 0, 3. The next one is going to be 0, 4. I'm just trying to figure out a quick way to use an equation to do this. So decimal to hexadecimal, and we are looking at 24 minus the row number. 24 minus the row number, and that should do it. Except, it doesn't give me the extra 0. Um, all right. Well, I guess sometimes you just have to do it the hard way, which is manually, assigning um, those addresses to these locations. So we have 0, 7, 0, 8, and doing 1, 2, 3, 4. Yeah, we need one more byte, which is 0, 9. All right. So the question is, what is happening with these memory locations? And I can make the column a little bit narrower, so this way we leave more space. So 0, 3 is the printer global variable. So we can just say, oh, this is what printer is. These two combined is global variable A. So this is global variable A. These two combined is global variable B. And then these two combined is global variable C. That's because your global variable A is a structure. So it has a member I and a member P. And global variable B is the same way. It has member I, member P. C has the same arrangement. It has member I and member P. So that accounts for the memory locations from 0, 3 to 0, 9. And then we can start from the top. So when we start from the top, um, there are no local variables in this particular program. So FF, is going to be used to push the argument to call traverse. And in the program, we were using the address of A. So if you look at A, it occupies 2 bytes. The address of a structure or anything that is multi-byte is always referring to the least address. So we are looking at location 0, 4. So that means, the actual content at location FF is 0, 4. And that is basically oh, okay, it doesn't like that. It's 0, 4 because it is the address of A from the perspective of main. But when you look at it from the perspective of um, traverse, it is actually parameter P of traverse. And then we have the return address. Okay, so the return address is, we can look it up too, because we can go back to the assemble tab and figure out where we're supposed to go back to after we call traverse. All right, so this is where we call traverse right here, the JMPI instruction. And then when we get back, we're supposed to get back to location 57. So that's how we know this location here is supposed to get a value of 57 in hexadecimal, because it is the return address. All right, so this is also really kind of important, is when we continue execution in the function traverse, this is where the stack pointer is pointing to. So the stack pointer is actually pointing to the return address, and the parameter is at one location higher than where the stack pointer is pointing to. And this is also why um, the way we access parameter p is to add one. We first copy the immediate value of 1 to a register, and then we add register D, which at this point of time is FE, to register A, which has the number of bytes between where the stack pointer points to, which is location FE, to the location where the parameter P is, which is FF. So that, I hope that explains the calculation. And this picture is particularly useful if you want to correlate it with the analysis tab for those 6 instructions that we were talking about, because then you can look at this, you can look at the actual effect of this, and then you can cross reference that to the actual mapping of memory. All right, so the next thing I want to do is to kind of show you how things get updated, and how the other instructions work. So the next part of the program I want to illustrate is how we are updating P itself. So the first part is updating printer. We verified that part already. But the second part, starting with um, line 69 in the TTP ASM code, is trying to override parameter P with member P of the structure that parameter P itself is pointing to. All right, so we first want to find out exactly what should happen. And in this case, because parameter P is 04, it is pointing to location 4. This is the structure that P is pointing to. But we are not interested in the entire structure. We're only interested in what member P has. So if I go back to the code and finish the initialization, I think the value of this is 05. So member I has a value of 05, and then the pointer member, the P member of global variable A as a struct node, as a struct X, sorry, has the address of B. So that would be 06. And then with B, I think I was initialized to 01. And then the member P is pointing to global variable C. So we can see how global variable C is starting at location 08. So that means member P of B is going to be 08. And then for C, the I value, or the member I of C, is going to be 7. And then member P, which is the pointer to the next struct X, is 00 to designate, to indicate that we are at the end here. All right, so let's find out how we got to this thing here, because eventually we have to copy this to parameter P on the stack. So what we do is we start with parameter P, or we start with the offset. So the offset is really just the gap between these two rows, which is 1. And then we add it to the stack pointer. The stack pointer is still pointing to location FE. 1 plus FE is FF. So at that point, we have the address, not so much the content, but we have the address of parameter P. The load instruction is dereferencing the pointer. So from the address of FF, now we retrieve the value of 04. Once we get to the value of 04, which is pointing to the first byte of the structure that is global variable A, we also load 1 into register B. That one is looking at the difference between the member that we want to access from the beginning of the entire structure, and the difference is only but 1 byte. And that's what that 1 byte is, when we load it into register, I believe it's register B. So when we add register B, which is 1, to register A, which is 04 at this point, then we get 05. But if you look this up, 05 is basically the address of member P of the structure that we know as global variable A. So that's the address. When we do one dereference, then we get to the value at that address, which is 06, and that is when we know what to use to update the parameter. And that's why parameter P of traverse would change from 04 to a 06. And then we keep doing this, right? So when this changed to 06, okay, let me just pretend that we are executing the program like that. That changes to 06. So in the next iteration, we look at 06 and ask, is it 0? The answer is no, it is not 0. We get back into the loop, and then inside the loop, the first thing we do is we retrieve member I of the structure that parameter P is pointing to. So we look at this 06 and say, let's go to the location 06. The location 06 is the beginning of a struct X, and then we say we want to access member I. Member I is the first member. It has a value of 01, and that's the value that we copy to printer, the second value that we copy to printer. And then in the second statement inside the while loop, we try to access member P. So we redo the entire thing. So we look at the displacement from where the stack pointer points to parameter P, which is 1. We add the stack pointer to that 1. So that means that register A, if I remember correctly, is going to have a value of FF. We get to 06. Okay, so at location FF, we dereference to get to the value at that location, which is 06. And then we load 1 into register B, which is measuring, from the beginning of the structure to the member that I need, how many bytes are in between. Only 1 byte. So we add that 1 to the address of the structure, which is 06. So we end up with an address of 07. And then at that point, we dereference, we get to the value, which is 08. And then we use that to overwrite parameter P. So parameter P changes to 08. And then at that point, we do this whole thing one last time. So we go to the first statement inside the loop. It uses this location combined with the displacement of member I from the beginning of the structure to know that the address of member I of the structure that P is pointing to is okay, I take it back, it's here, and it has a value of 07, and that's why 07 is the third update to the global variable printer. And then on the next statement, we do pretty much the same thing. We look at the structure that P is pointing to, which is this structure here. And then we say, but we only need to access member P. The value of member P is 00. So we use that to override local variable, not local variable, but parameter P. So parameter P becomes 00. We go back to the beginning of the loop. It calls cond, and cond is just returning the parameter. And if the parameter is 00, it just returns 00. And inside the condition of a loop, 00 is interpreted as false. And as a result, we get out of the loop. And that's the end of it. Okay. So that's an explanation of how this code executes. So in class, I also emphasized that the code that you see in the final exam does not necessarily have to look like the code that I'm giving you here. So the idea is, okay, this code here. So the idea is I have to play by the same rules. Okay, what are the rules? I can even look at the program and tell you what the rules are. So the rules are, the way we The way we assign locations within a structure for its members is simply to look at the ordering of the members within a structure, and we just say, if member I appears first, then it is the first member, and then if member P is the second one, then it is after I. So the offset of each member from the beginning of a structure is really just sequential to how the structure itself is defined. What you do have to pay attention to is how big is a particular member. Now, up to this point, all the members only have a size of one because an unsigned 8-bit integer only has only uses 1 byte, and then any pointer only uses 1 byte too. So that's why we see this one over here. Let me Okay, there we go. So this one is referring to the size of member I, and this one here is referring to the size of member P. And it doesn't have to be exactly one. Okay, so there are some types where the number of bytes for that member can be different. And then the second thing that we which is okay. The second thing that I can always count on, it's not going to change in the exam, is how we um, implement global variables. So global variables are nothing more than just a label followed by some byte code. Each byte code is basically just allocating a particular byte and say what is the initial value of that byte. So printer as a label is corresponding to the location of this particular byte, and then the next location, which is this 7 here, has a label of C. And this particular location has no particular label associated with it. You can call that C plus 1, but there's no single label to define that location. So this is the other thing that I would not change, is how initialized structures are represented in TTP ASM. So the way it is organized is actually dictated by the structure itself. So the first byte is corresponding to member I, and then the second byte is corresponding to member P, and that's how global variables are allocated and also initialized. So we now account for C, B, and A in the C code in assembly code. What I also will not change is how the stack is organized when you are the caller callee agreement will not change. So the thing is the caller is responsible to push parameter push all the arguments first and then push the return address. So that means on the stack you will find the arguments first. In this case, there's only one, and they will find the return address. When I said that, P is the one that has a higher address, and then return address is the one that has a lower address. And the stack pointer, by the time you get to the entry point of a subroutine, is at the entry point, the stack pointer is always pointing to the last thing that was allocated or pushed on the stack, and it is always the return address. That's the caller callee agreement, and that agreement will not change in the final exam. This is still going to be a constant. Okay, it is not going to change. All right, when we're getting into a subroutine, the subroutine can make use of registers A, B, and C any way it sees fit. It sees fit. So that means the caller cannot assume registers A, B, or C is going to be preserved when a subroutine is called. The subroutine is under no obligation to preserve those particular registers. Local variables, if any, is the responsibility of the subroutine being called to allocate. So we can see line 25, 26 is for allocation, and then line 32, line 33 are for the allocation. Using a label, like in this case, local var size, to indicate the number of bytes that we need to allocate is really handy because this way I don't have to remember or keep track of the number of bytes to allocate and also the number of bytes to deallocate. However, that is not a part of the caller callee agreement. This is simply a way for me to implement the agreement itself. So that means how I allocate, what instructions I use to allocate and deallocate for the local variables. That doesn't have to be the same as what is displayed here in the final exam. That can change. And then how we access the local variable or the parameters is also the method can change, but the where we can find them on the stack will not change. So in other words, I'm where the destination is does not change, but the route to get there can change. So the route that I show you here is one route, but there are other ways to do the same thing, and those other ways were actually discussed in the modules. And some of the earlier sample programs to talk about how to access parameters and local variables use the other method, which is a little bit messy. It requires you to really kind of be careful and keep track of um, what each register has at any particular time. So that's also legitimate in the final exam. Okay, the final exam, the way I access the parameters and also local variables doesn't have to be clean like this. All right, it is the responsibility of the callee to pop the return address. That part is not going to change. However, the actual sequence of instructions to do that pop, that can change. In other words, the effect is the subroutine being called is responsible to deallocate and make use of the return address. That part is not changed, cannot change. What can change is the way I do it. All right. So that means you're just memorizing and pattern matching these three instructions. Excuse me. Always has to be at the end of a subroutine. That's not going to work because I may not use exactly the same mechanism in the final exam. But you have to understand that but what it is achieving is not going to change. All right. So that pretty much goes for the second subroutine as well, traverse, which we just talked about. The way a loop works is this is the general template of a while loop. So you need to go back to the module and also the lectures, that talk about how control structures are translated into assembly language. The tricky part is, what about the condition? Because in this case, the condition is a call to a particular subroutine. So it is basically a combination of two concepts that we have talked about, which is we have to check whether the condition is true or false. If it is false, we get out. If it is true, then we do not get out, right? So that part doesn't change, but how we know whether the condition of the while loop is true or false, that really depends on the expression inside the parentheses of the while. Excuse me. Um, so that part I really cannot give you a general template of how to get it done. All right, calling a subroutine. How do you call a subroutine? The effect is we need the arguments to be on the stack in the order of the last argument has the highest address, the first argument has the lowest address. That's the effect. The effect is not going to change because that's part of the caller callee agreement, so that is not going to change. But the instructions that I can use to implement that doesn't have to follow exactly the same way that I do it here. And then we have the pushing of the return address, same deal. Okay, so typically we use line 53 all the way to line 55 to specify how to push the return address on the stack. Now you can also probably remember earlier in the class we use a label to designate the point where we need to return to. So that's basically just another way to push or specify the return address. So the effect, once again, is to push the return address on the stack. The implementation of using decrement LDI store, that doesn't have to be exactly the same. Okay, so you have to keep in mind that using pattern matching is not always going to work. You really want to kind of figure out what is in the register at any particular time, and also understand what the program is supposed to do. What is the intended effect? That's important. Okay, and then you compare and then you track the registers and what it's doing to memory to make sure that that is achieving the effect that we want. That would be the essence of the final exam is you have to know what the effect is supposed to be, and then you track the instructions and the registers and memory content to make sure that the code is doing what we're supposed to do. Pattern matching, what I show you here, well, can probably get you some points. Okay, I'm not exactly sure how many because I have no idea what the final exam is going to be just yet. But the important part is, what is the effect? How do I know whether a sequence of instruction achieve a particular effect? If it does not, then the question is, how do I fix it? All right, so I think that pretty much is the essence of the final exam. Is it is not about pattern matching. It is about you understanding, showing me that you understand the effect of how to implement all the C concepts in assembly code, and that's what I'm testing. Okay, and that's where you need to put your focus on, is really to understand all the instructions in the context of the C code, and understand how what is happening in memory, and also if there's a problem, if it's not achieving what is supposed to be done, how do we fix it? Am I giving you an extra instruction? Am I missing a particular instruction? Am I using the wrong register? Am I using the wrong label? Am I using the wrong flag? All of those can potentially happen. All right, so I think this is pretty much a recreation of the lecture on Thursday, and I'm going to stop the recording now and get it uploaded.